The formation and evolution of the Moon have long fascinated scientists and laypeople alike. The Moon, our planet's only natural satellite, has played a significant role in shaping our understanding of planetary science, gravity, and the broader universe. While it appears to be a simple and unchanging celestial body when observed from Earth, the Moon's story is one of violence, complexity, and intrigue, stretching back billions of years. Around 4.5 billion years ago, shortly after the formation of the solar system, Earth was struck by a Mars-sized body in what is now known as the giant impact hypothesis. This catastrophic collision ejected vast amounts of debris into space, which coalesced to form the Moon. The aftermath of this event saw the Moon initially as a molten body, slowly cooling and solidifying over millions of years. This nascent Moon was bombarded by asteroids, resulting in numerous craters and shaping the Moon's early surface. The Great Bombardment and early lunar surface formation. About 4 billion years ago, the Moon experienced a period of intense bombardment, where countless asteroids and comets rained down on its surface. This epoch, known as the Late Heavy Bombardment, left the lunar surface riddled with craters. The bombardment was so extensive that it tore into the Moon's outer crust, especially in areas where the crust was thinner. In the Moon's early history, its interior was still hot, and molten magma from within the Moon seeped through the fractures in the crust caused by the impacts. This molten material spread out into vast pools on the Moon's surface and then solidified, forming large, flat plains of basaltic rock. These flat, dark regions are what we now refer to as the lunar maria, singular, mare. These maria are especially prominent on the side of the Moon that faces Earth, giving the near side its distinctive appearance with dark patches interspersed with brighter highlands. One of the most curious aspects of the Moon is that, despite rotating on its axis, the same face of the Moon always points toward Earth. This phenomenon, known as tidal locking, occurs because the gravitational interaction between Earth and the Moon has caused the Moon's rotation period to synchronize with its orbit around Earth. As a result, from Earth, we only ever see one hemisphere of the Moon, while the far side remains hidden from view. For centuries, the far side of the Moon was a complete mystery. No human being or machine had ever observed it. From Earth, early astronomers could only speculate about what the far side looked like. Many assumed that it would be similar to the near side, with its dark maria and bright highland regions. However, this assumption was shattered in 1959 when the Soviet spacecraft Luna 3 became the first to photograph the Moon's far side. The discovery of the far side, a lunar mystery unveiled. When the first images of the far side of the Moon were transmitted back to Earth, scientists were shocked. The far side of the Moon looked entirely different from the near side. Instead of the familiar mix of dark maria and lighter highlands, the far side appeared almost uniformly bright, with far fewer maria and a much higher density of craters. The far side was heavily pockmarked with massive impact craters, but it lacked the dark, flat plains of basaltic lava that are so prominent on the near side. This discovery raised numerous questions. Why was the far side of the Moon so different from the near side? Why were there so few maria on the far side? And why were the craters on the far side more uniformly distributed? One of the key observations that helped to solve this mystery was the realization that the crust on the far side of the Moon is much thicker than the crust on the near side. Recent NASA missions, including data from the GRAIL, Gravity Recovery and Interior Laboratory, mission, confirmed that the far side's crust is approximately 30 miles thicker than the crust on the near side. This difference in crustal thickness provided a potential explanation for why the near side has so many maria while the far side does not. On the near side, where the crust is thinner, molten magma from the Moon's interior was able to break through the surface more easily, filling in craters and creating the large, flat maria. In contrast, on the far side, the crust was too thick for magma to easily break through. As a result, impact craters on the far side remained unfilled, and the surface is dominated by heavily cratered highlands rather than smooth maria. However, while the crustal thickness provided part of the explanation, it raised another question: why is the Moon's crust thicker on the far side than on the near side? Theories related to the giant impact that formed the Moon could not fully explain this discrepancy. According to the giant impact hypothesis, the Moon formed from the same pool of debris, so its crust should be more or less uniform. Something else must have happened to create this dramatic difference between the near and far sides of the Moon. One of the most intriguing explanations for the moon's asymmetry is the dual moon hypothesis, which suggests that the Earth may have once had two moons instead of one. According to this theory, shortly after the giant impact that formed the moon, two separate bodies formed from the debris, a larger moon, which is the one we see today, and a smaller moon, which orbited alongside it. Over time, this smaller moon would have slowly drifted closer to the larger moon. Eventually, the two moons would have collided in a slow-motion impact. Instead of a high-speed, catastrophic collision that would have shattered both moons, the smaller moon would have gently merged with the larger one. This collision would have occurred on the far side of the larger moon, leading to the thickening of the crust in that region. The dual moon hypothesis provides a compelling explanation for why the crust on the far side of the moon is so much thicker than on the near side. The smaller moon essentially smeared out over the far side of the larger moon, adding to its crust and creating the asymmetry that we observe today. In this scenario, the near side of the moon, which was not directly impacted by the smaller moon, remained relatively thin, allowing lava from the moon's interior to seep through the surface and create the Maria. The far side, on the other hand, was covered by the remnants of the smaller moon, resulting in a much thicker crust that prevented lava from escaping. When we look at the moon today, according to this theory, we are essentially seeing the remnants of two celestial bodies. The near side reflects the surface of the original, larger moon, while the far side carries the scars of the smaller moon that merged with it. Modern confirmation and future exploration. In recent years, data from lunar missions, including NASA's Lunar Reconnaissance Orbiter and the Grail mission, have provided further evidence to support the idea that the moon's far side has a significantly thicker crust. These missions have used high-resolution gravity mapping and topographic data to build detailed models of the moon's internal structure, revealing the variations in crustal thickness across the lunar surface. The Chinese Chang'e 4 mission, which landed on the far side of the moon in 2019, has also provided new insights into the geology of the far side. As the first mission to land on the far side of the moon, Chang'e 4 has offered a unique opportunity to directly study the far side surface and collect data on its composition and structure. Scientists are still working to fully understand the processes that shape the moon's formation and evolution. The dual moon hypothesis is just one of several theories that attempt to explain the moon's asymmetry, and ongoing research and exploration will continue to shed light on this fascinating celestial body. Conclusion: the moon's complex history. The moon, often thought of as a simple, unchanging object in the night sky, has a rich and complex history that is still being unraveled by scientists today. From its violent formation in the aftermath of a giant impact to the possibility that it once had a smaller sibling, the moon's story is one of continuous change and transformation. The discovery of the far side of the moon in 1959 marked a turning point in our understanding of the moon's geology, revealing that it is far more complex than we had previously thought. The far side's heavily cratered surface and thick crust stand in stark contrast to the relatively smooth Maria of the near side, and scientists have been working for decades to explain this dichotomy. The dual moon hypothesis offers one possible explanation for the moon's asymmetry, suggesting that a second, smaller moon once orbited Earth alongside the larger moon before slowly merging with it. While this theory is still under investigation, it provides a fascinating glimpse into the dynamic processes that shape the moon's formation. As technology advances and new missions continue to explore the moon, we can expect to learn even more about the history of our nearest celestial neighbor. Whether through the study of ancient impact craters, the analysis of lunar samples, or the exploration of the moon's far side, the moon will continue to captivate and inspire future generations of scientists and explorers.